recapping from last lecture. Okay, so last time we talked about reduction of order. Okay, and it simply said that if you have solutions from differential equations, let's say one solution, then you need to find just the other n-1 solution. Okay, for this example, 4.14, you are given already one solution, which is y equal to x, so that the given differential equation is in second order. So it means that you have to find another n-1, which is 2 minus 1. So just one more solutions. Okay. So the order of these differential equations is actually reduced to reduced to n-1, which is 2 minus 1, which is 1. So simply this second order, if you know one of the solution, it will reduce to just first order, and you can solve the first order differential equation already. Okay, so for this example, you are given the solution y equal to x. That would be the solution of x squared plus 1 times d squared y by dx squared minus 2x times dy by dx plus 2y equal to 0. So this equation is second order, and you need two linearly independent solutions, right? And if you have that linear independent, you can find a general solution. One of them is given, so f of x equal to x. You need to find another one, and then you can form the general solution. Okay, so to find another one, you need to transform by this transformation, f of x. Okay, I use another color. F of x times v equal to y, and then you have to plug in for every values of y in the differential equations given. So you need to find d squared y by dx squared, you need to find dy by dx, you need to find y, right? And when you plug it in, the noticed term would be the last term that should be equal to 0. So here we have minus 2x plus 2x equal to 0. If this is the case, it means that we can have shows w equal to dv by dx, right? Substitute dv by dx by w, and substitute d squared y by d squared v by dx squared by dw by dx. So literally, this second order of d squared y by dx squared is reduced to just first order. So once you have the first order equations, you can solve for it, right? Now it's back to the previous lecture, previous section that we have learned how to solve the differential equation for first order. Once you solve for these differential equations, you will end up with some constant c. And normally we're going to set that c equal to 1, okay? And we said, and we're going to have the answer in w term, okay? However, we don't want w. We would like to have v, such that we can substitute v for y equal to f of x times v, and then we get y, which is the ultimate solution that we want. So we have w equal to dv by dx. It means that we can find v by integration of w dx. All right. So when we integrate them all, you get v, and then you put v for this transformation, and you get another solution for these differential equations. Okay. After that, just put them into the general solution form, c1 times f plus c2 times g. This is the equations of the general solution for this example. Okay. Today, you're going to move a bit to the non-homogeneous equations. The non-homogeneous means that you got the right hand side, okay, f of x not equal to 0, right? If this term equal to 0, these equations would be homogeneous. If this term is not equal to 0, it's going to be non-homogeneous, right? So we're going to talk about the basic theorem that are concerned with these non-homogeneous equations. So we have the hypothesis said that if we have any solution V, right, V given to these non-homogeneous n order linear differential equations, okay, so we are given V for the non-homogeneous, and secondly, we are given let U be any solution of the corresponding homogeneous. The corresponding homogeneous means that you would have the left-hand side of these two equations. This is the first equation and the second equation. Those two equations, you would have the same left-hand side. However, the right-hand side in the second equation would be 0 because it is homogeneous. The corresponding means you get the same left-hand side, and homogeneous mean you got 0 at the right-hand side. Okay. Now, if those two hypotheses are met, then you can say that U plus V is also a solution to the non-homogeneous. Okay, let me get this straight. So you have non-homogeneous differential equation, let's say n order. So it means that something equal to f of x, right? This is n order dE. And the corresponding homogeneous differential equations would be n order, the ODE, the same. But the second one would be equal to 0 because this one is homogeneous, right? And if this one has V as a solution, right? Okay. This one has U as a solution. The theorem said that V plus U would be also a solution to the non-homogeneous. Okay, this is what it said. All right, let's do this example so you see what they mean. Oops. Okay, so 4.15, you have y equal to x is a solution. This is for non-homogeneous, right? And the equation is d square y by dx squared plus y equal to x. Is non-homogeneous because f of x not equal to 0, all right? And another solution is y equal to psi of x. This is a solution to the corresponding homogeneous, right? So corresponding means you get the left-hand side Oops. It's the same, but the right hand side you get 0. Okay, so the theorem said that if you have this as a solution to these equations, you have this is a solution to this equation. So V plus U would be a solution to non-homogeneous. So let's try to prove that. Okay. So if we take V plus U, you would get X plus psi X. Okay. And we would like to substitute in the homogeneous differential equation. This one. Okay. We have already y, so we're going to need to find d squared y by dx squared, or the second derivative. So this y equal to x plus psi x, when we find the first derivative, you would have 1 plus the, what is the derivative of psi? You can text me. Derivative of psi. Cosine of x, okay? And we're going to need the second derivative. Thank you. So the first term is constant, that would become a 0. And the derivative of cosine would be minus psi of x, okay? So let's try to put that in the original equations. D squared y by dx squared would be minus psi x plus y is x plus psi x equal to x. And you can see right away that this equation is satisfied. You get x equal to x, so the left-hand side equal to the right-hand side, and this y equal to x plus psi x would be the solution to the non-homogeneous d squared y by dx squared plus y equal to x equations. All right. So this is how they show that the theorem is working. Okay. All right. Now we can apply the theorem in case where V, right, is a given solution called YP. And this is the solution to the non-homogeneous equations. And you have no arbitrary constant. For U, this is the general solution. So U equal to C1y1 plus C2y2 until Cn_yn. And this is for corresponding homogeneous equations. Or in other words, for non-homogeneous, you said that V is a solution, right? For corresponding, V is actually YP, right? For corresponding homogeneous, you get U, which is the general solution, and we call that YC is a solution. So the theorem said YP plus YC is going to be the solution to the non-homogeneous as well, right? So YP plus YC would be solution to the non-homogeneous equations, right? This is from the theorem. And we also have n arbitrarily constant C1 until Cn, okay? So let's put that in the hypothesis, in the theorem. Hypothesis said that if we let YP be a given solution for n order non-homogeneous linear equations, you have no arbitrary constant, and you let YC equal to these linear combinations, which is a solution of the corresponding homogeneous equations. If those two items of the hypothesis are satisfied, then we can conclude that every solution, let's say phi, of this nth order can be written down in the nth order non-homogeneous equations can be written down as yp plus yc. And yp is just this term, but yc is all of these linear combinations, okay? And this is called a general solution for the non-homogeneous differential equations, okay? Before we have homogeneous, right? And our general solution would be, let's say, F C1 F1 plus C2 F2 and so on plus CMFN. This is n nth order, right? Now, if we have nth order non-homogeneous, the general solution would be, or not F, sorry, should be Y, would be YP plus YC, okay? So the general solution Y would be YP plus YC. And the YC itself is actually C1 F1 plus C2 F2 until Cn Fn, okay? Oops. Okay. So we have used the general solution, the same word, but you have to see whether that's the general solution for which type of the equations. If it is a homogeneous differential equations, then the form would be like this, right? If it is the general solution for the non-homogeneous, then you have this form, okay? Now let's consider nth order non-homogeneous linear differential equations. So non-homogeneous mean fx not equal to 0. And also the corresponding homogeneous, which is the same left-hand side, but the right-hand side equal to 0. What is said here is that the general solution of the corresponding homogeneous equation is called contemporary function. So this is YC, right? This is contemporary function of the non-homogeneous equation, right? And you have also particular solution of the non-homogeneous equation, which has no arbitrary constant, and this is called particular integral of the non-homogeneous equation, and this is called YP, okay? General solution would be YP plus YC, that's all, okay? So, if we're gonna apply this theorem, we're gonna need to find, if we would like to find the general solution of the non-homogeneous equations, we're gonna need to find two things. The first thing is complementary solution. This is a general linear solution, a linear combination of n linear independent solution of the corresponding homogeneous. And actually this is YC. Another terms you're going to need to find is particular integral. And this is particular solution of the non-homogeneous equations without any arbitrary constant. So put it down more easier to understand. You have non-homogeneous general solution. So it's going to be y equal to yc plus yp. This yc is called complementary. Functions, and this yp is called particular integral. This yc is general solution of corresponding homogeneous equations. Okay, so this is going to be the structure, right? So to find the general solution of non-homogeneous differential equations, you need two terms, right? The first term comes from the general solution of the corresponding homogeneous, and another term is particular integral. Okay, let's see this example. It said that you have the differential equations, this one. So this is non-homogeneous, right? Second order, right? Non-homogeneous because the right-hand side is not equal to 0, and you get the second order here. And you are given the complementary functions of this non-homogeneous differential equation, which is a solution of this corresponding homogeneous. And again, the left-hand side is the same, but the right-hand side, for the corresponding homogeneous, you got 0. Okay, so particular solution is given by yp equal to x. How do you find the general solution? So this is easy, right? The general solution would be two terms in combination, yp plus yc. Yp is already given, which is x. Yc is also given, so it's c1 psi x plus c2 cosine x. So this would be the general solution for non-homogeneous second-order differential equations. This one. You can try to prove that. Let's do that. So here, if we want to prove that this is a solution, we're going to need to find the second derivative. So let's take the first derivative. This is going to be 1 plus c1 cosine of x plus c2 minus psi of x. Okay, and we need to find the second derivative. So this is the constant, we get a 0. And then we have c1 minus psi of x minus c2 cosine of x, right? Now we have everything. We put it back into the original equations. So we have minus c1 psi x minus c2 cosine of x plus y. Our y would be x plus c1 psi x plus c2 cosine of x equal to x. And you can see that those two terms, they cancel out, and we have x equal to x, which is proof that y is the general solution. Okay. Okay. Now, if the non-homogeneous member of f of x, it means on the right-hand side, is expressed as a linear combination of two or more functions. For example, this is the same left-hand side with f1. And then you have this same left-hand side, but with f2, right? So those two functions are different, right? But those are the non-homogeneous differential equation. If this is the case, then you can use the following theorem to find the particular integral. So to find yp, okay? And this is the theorem set. You have f1, which is particular integral, or yp, of these equations, right? And you have f2 as a particular integral of this equation. They are different because you have different function of the right hand side. The first one you got f1x, the second one you got f2x. However, the particular integral can be found by using k1 f1 plus k2 f2. Okay, so when you combine those equations, the right hand side becomes k1 f1 plus k2 f2, where those two k's are constant. Okay. Okay, let's see this example. So we are seeking for particular integral, so yp, of these differential equations. And you know that this is the combination of the two right-hand side, right? So the corresponding equations for A would be d squared y dx squared plus y equal to 3x, right? This is the first equations. The second one would be d squared y by dx squared plus y equal to, should be x equal to tan of x. This is the second, right? The second equation. So this is, not this. This is f1 of x, and this is f2 of x. Okay. And theorem said the solution, the particular solution, particular integral of d squared y by dx squared plus y equal to 3x plus 5 tan x is k1 f1 plus k2 f2. And it said here that the particular integral for the first one would be y equal to x, right? So here, solution is y equal to x. Here, the solution is minus cosine of x ln sec x plus tan x. Okay. So if we have this, we can use this theorem to find yp. So yp would be 3, right? This is k1. Oops. This is k1. And 5, this is k2. So 3 times x, this is from the first solution, plus 5 times minus cosine of x ln sec x plus tan x. All right. Okay, so this would be the particular solution. So we haven't done anything. We just said that if the right-hand side is the combinations of two functions, f of x, f1 of x, f2 of x, then the solution would be the combination of the solution from each equation with the same coefficients here. Okay. Okay, now we gonna go back to the homogeneous linear equations, but now we just consider for constant coefficients. So you can see that before you have this equation in form of a0 of x, right? So this is mean a sub 0 is a function of x. For example, x or x squared or x plus 1 and so on. But now you have a sub 0 equal to some constant, right? So just a number. There's no x here, right? So a sub 0, a sub 1 until a sub n, all of them are constant, okay? So this is more like a special case for the linear equations of the homogeneous linear differential equations, right? You just consider only the case where the coefficients are all constant, and also it has to be the real constant. Real constant. This is important. Real constant, right? So we do not consider the coefficients to be like complex number, right? It has to be the real number. Now, we should show that the general solution of these equations can be found explicitly. Remember, the goal for solving these differential equations in higher order is to find the general solution, right? And if you're going to have the general solution for the homogeneous differential equation of n order, it means that you're going to need to have n linearly independent solutions. Okay, if you have n linearly independent solution, you can take the linear combinations to get the general solution. Okay. Now, how can we do that? How can we find it? So, said here that in the attempt to find the solution of a differential equations, we would naturally inquire whether or not any familiar type of function that we might have, that might possibly have the properties which can be a solution. So it's kind of not inconcise. So this is just say that you want to find some function which can be a solution, all right? And it has to have some properties to be a solution. So for this differential equation here, for these differential equations here, so it's n order, and you have the constant coefficients. So if you have f, right? If you have f as a solution, your f should have the following properties. First, you multiply the function with its derivative by certain constant, and then you get the constant times the derivative of f. Okay? And when you sum them all, you get the 0. Okay, so you can see that from the equations here. Okay, let's take a look for second order just to make it more easier to see, right? A sub 0 plus a sub 1 dy by dx plus a sub 2 y equal to 0. And let's say f is a solution. So what property f should have to be the solution for this? Okay. So y equal to f. So I put f in here. I would have a2 times f, right? a2 times f And then I take derivative of f. I would have some constant, right? Should have some constant times the function of f with n minus I. It's going to be 2 minus 1. So it's going to be the first derivative of f. Okay. And here would be some constant times the second derivative of f, right? Because I put not some constant, the a actually, a sub 0, a sub 1. Okay. And then when we sum those terms up, we need to have 0, right? So this is the properties of the function that we would like to have. First, when you multiply the function and its derivative by the certain constant, like this constant, you get this term, right? And when you add those terms up, you should have 0. So if this is the case, then your f is the solution to these differential equations, right? That's what it said. So to have these properties, we're going to need a function such that its derivative are constant multiplied by itself. Why is so? Because if, let's say, your solution is f, your first derivative of f would be some constant. Let's see, c1 times f, right? And then the second derivative would be some constant times f as well, right? If this is the case, and when we plug it in, you're going to have a sub 0 times c2, which is actually a constant, times f, right? Plus a sub 1 times c1, actually some constant, times f, plus a sub 2 times f equal to 0, right? So the thing here is that we're going to need to find the right coefficient such that these combinations get you to 0, right? So if we have the function such that when we take the first derivative, you get some constant times the very same function. And if you take the second derivative, you get some constant times, again, the very same function. Then you can put into these equations and you can solve for the coefficients and you get the solutions, right? Okay, the question is, do you know such functions? The functions that when you take k derivative of the function, you get some constant times that functions. Any idea? Can you tell me any idea? Silent. So suppose let's try f of x equal to x squared. So what is f prime? What is f prime? What is f prime? No idea. What is f prime? 2x. But this cannot write down as some constant times f, right? Because this is x squared. So it's different functions. So x squared might not be the case. Can you find some function that when I take the first derivative, I get some constant, let's say, times the very same functions? Yeah, e to the power of x, for example. So let's say f equal to e to the power of x, right? F prime is going to be e to the power of x, or f in the what they want to see is 1 times f. Or you can have f equal to e to the power of 3x, let's say. So f prime would be 3e to the power of 3x, which is 3 times f, right? So we have constant times the function. Furthermore, if we take the second derivative, you will get 9 times e to the power of 3x, which is 9 times f. So we have some constant times the function. So this is what we are looking for. Okay. So seems like e to the power of x satisfy these properties. Okay. And it's said here, if we take e to the power of mx and we take k derivative of these functions, this is what you're going to have. M to the power of k, e to the power mx. Okay. So we shall seek solution of homogeneous linear equations with constant coefficients, right? This is with constant coefficient in this form. Why? Because we already see that if this is the case, we're going to have to solve just because f can be cancelled, right? And you can solve just the coefficients to find the right coefficients. And then we get the 0 equal to 0. All right. So the problem would be finding the constant m such that e to the power of mx satisfy the equations. Okay. So let's see. Okay, let's put another page here. Okay, so you actually have d to the power of n y, right, by dx to the n plus, oh, actually a sub 0, a sub 1, d to the power of n minus 1 y dx to the power of n minus 1 until you have d to the power of d square y by dx square plus, this is I think it's a n minus 1. I think it's a1, right? And you get, oh, sorry, should be a n minus 1. That's correct. A n minus 2. Let me check. Yeah, a n minus 2. This is a n minus 1 dy by dx, and then you have a n y equal to 0, right? And we say let y equal to e to the power of mx, right? So a sub 0. So you take n derivative of e to the power of mx. What you're going to have is m to the power of n times e to the power of mx, right? Because every time you take the derivative m, you take derivative n times, you get m to the power of n. Okay. Plus a1 m to the power of n minus 1 e to the power of mx. Okay. So on until a n minus 2 m to the power m square times e to the power mx plus a n minus 1 m e to the power mx plus a n. So just e to the power mx equal to 0. Okay. So you just take y and put it right into the differential equations in order. And because e to the power of mx will never be equal to 0, so we can divide all of those terms by e to the power of mx. right? So that term would be gone. And what we have left would be a sub 0, m to the n, plus a1, m to the n minus 1, plus, until an minus 2, m square, plus a m a n, not m, a n minus 1, m, plus a n equal to 0. Okay, so this is what we're going to have, which is exactly these equations. Okay, and this equation is called auxiliary equations or characteristic equation of the given differential equations, right? So this is very important. So if y equal to e to the power of mx is a solution, now we need to find a constant m that satisfies the characteristic equations. So we can observe that we just seems to replace the n derivative with m to the n, right? The n minus 1 derivative with m to the n minus 1. The second derivative by m squared. First derivative by m. And no derivative with m to the power of 0, which is 1. Okay? So it's turned out to be very easy to solve the homogeneous differential equation with constant coefficients. We actually turn these differential equations into the corresponding characteristic equations, right? And we solve for this equation instead. Okay. Now, based on that, the equations, I mean, the solution would be y equal to e to the power of mx. So once you can solve for m, you need to put m here and you get the solutions, right? Okay. Now, in this case, you would have 3 different cases arise. For example, if your order is 2, let's say you're gonna get m squared plus m plus, okay, let's do this, am squared plus bm plus c equal to 0, right? This is the characteristic equation of the second order. Okay. Now it said that you have 3 possibilities. How do they come? You have any idea? Remember, we would like to find m. Or in other words, you would like to find the root, right? This is the root where something equal to 0 is to find the root. Or simply solve for m. How can you solve for m? Can you tell me? How can you solve for m? This is high school math. Yes. Do you remember the formula? How to solve for m? Quadratic, right? The formula would be m equal to great minus b, all right? Plus minus the square root of b squared minus 4ac over 2a. All right, this is the solution to this. But how come you get 3 cases? How do you get those 3 cases? You have just one solution. How do you get those three cases? What is the first case? Real, distinct roots. What does it mean? How do you get this first case? In what conditions you're going to get this first case? Any idea? Okay, now you get to see that there's two real, and there's one complex, okay? Complex root. What can make these equations being a complex number, complex roots? Which part of the equations make it to be complex root? Or when it can be the complex number? In which condition do you have the complex number? Negative what? Yeah. So, okay, the third one, you're going to have the negative number inside the square root, all right? So what does it mean? It means that b squared minus 4ac less than 0. Okay, this is the case where you get the negative square root, right? So what would be the other two? What would be the other two? The first one, you have distinct. Distinct means not the same, right? And you got plus minus here. It's real, so it means that inside the square must be real number, okay? And to make it distinct, those real number must not be equal to 0, right? And it cannot be less than 0, so it must be greater than 0. So b squared minus 4ac greater than 0, okay? Of course, the only case left when you have the real and repeated root means that your m1 and m2, right? You have two, you have second order, you have two roots. So m1 and m2, with this one becomes 0, you would have m1 equal to m2, repeated root. So this is the case, b squared minus 4ac equal to 0, all right? That's why you get three different cases just from one equation. Okay, let's start from the first case, distinct real root, right? Distinct real root. Now, suppose the roots of the characteristic equations are n distinct, right? You have n root, right? You have n root for m to the power of n, right? Number of roots would be equal to the number of the order you have, okay? So you have n distinct real number. I mean, you have n distinct roots, so you have n order, and it's come from m1, m2 until mn. So the solution would be you put that into here, right? We actually have the form of the solution already, y equal to e to the power of mx. What we do not know is just m, and we find m from the characteristic equation, and we know that the roots of characteristic equation are m1, m2 until mn. So the solution of the homogeneous differential equation with constant coefficient would be putting m1 here. This is the first equations, the first solution. The second solution would be e to the power of m2x The third one would be e to the power of m sub 3x, right? And your n solution would be e to the power of m and x. Questions? Questions? Okay. Now, remember, we would like to find the general solution. If you can have the general solution, means that you're going to have to show that, I mean, in this form, C1, Y1 plus C2, Y2, and so on. In this form of general solution, you need to show that all those Y are linearly independent, okay? If all those Y are linearly independent, then the general solution can be stated in that form. So, what we do, we use the Wronskian determinant we have seen already, okay? And you just find the Wronskian. And if the Wronskian is not equal to 0, means all of these, they have linear independent properties. And then you can put them into this pattern to find the general solution, okay? So let's put that into theorem. You have nth order homogeneous linear differential equations with constant coefficients. And you have n distinct real roots, so m1, m2, mn. They are not the same. There's different numbers. Then the general solution can be found by the linear combination, right? C1 times the first solution, y1, which is e to the power m1x, plus C2, y2, which is e to the power m2x, and so on, okay? And those would be just the constant. Okay. Again, for nth order homogeneous linear differential equations with constant coefficients, you should have those conditions first. And you found that the roots of characteristic equation are real and distinct, then you can say that the general solution can be written down like that. Okay. So let's see this example. For point 19. Oops. So you would like to find the general solution of d squared y by dx squared minus 3 dy by dx plus 2y equal to 0. All right. So before you go further, what you need to have is the linear, the homogeneous linear differential equations, all right, with constant coefficients. Okay, right? This is the requirement of the theorem: homogeneous linear differential equations with constant coefficients. So, is these equations linear differential equations? To be linear means that you don't have the multiplication of y and its derivative, right? You don't have the derivative with some other power, like 2, 3 or so, just first power, and you don't have the transcendental function of the dependent variable. Remember that from the very first lectures, okay? So in here you have constant, you have none of those conditions. So it is a linear, it is a linear differential equations, right? Homogeneous, right? Because you got the right hand side equal to 0 with constant coefficients, okay? Because you got 1 here, -3, +2. So those are numbers. Now you get everything satisfied by the theorem. So secondly, you need to find the characteristic equation, right? And it's quite easy to find that because we just substitute the derivative with the m. Okay, so you have second derivative for the first term. It's gonna go for m squared, right? -3. First derivative, so it's gonna be m to the power of 1 plus 2, and then y is just m to the power of 0, so it's just plus 2, equal to 0. Okay, now what is the roots, or what is the value for m in this case? Can you give me the values of m in this case? Again, high school math, 1 and 2, 1 and 2. All right. So how they got 1 and 2? So you need to take the factors of that equations, right? So you got m times m squared, and then you have, -1 and -2. So when you multiply those, you got 2, right? You multiply those, you got m squared. And then you multiply that, you get -2m. You multiply those, you get -m. So essentially, you just factor out to have m-1 and m-2. So, okay, I put it down here, m-1, m-2 equal to 0. Now you have two numbers multiply together and you get 0. It would mean that m-1 equal to 0 or m-2 equal to 0, right? So which means m is equal to 1 or m equal to 2. That's two roots. And you see that this is real and distinct, okay? And the theorem said that if you have real and distinct, your solution, your general solution would be C1 e to the power of m1, which is 1 times x, plus C2 e to the power of m2, which is 2x. And that's all, okay? We get the solution. Let's check whether this is really a solution. So to check, we need to take the first derivative, right? And the second derivative, found that. Okay, let's try to take the first derivative here. So the first derivative of the solution would be C1 e to the x, right? Plus 2C2 e to the power of 2x. The second derivative would be C1 e to the x plus 4C2 e to the power of 2x. Okay, let's check whether this is work out. So the first term is d squared y by dx squared, or the second derivative, which is C1 e to the x plus 4C2 e to the power of 2x, right? And then you got -3 y prime. So -3 y prime is C1 e to the x plus 2c2 e to the power of 2x, okay? And then the last term is plus 2, right? Plus 2, which is c1 e to the x plus c2 e to the power of 2x, okay? And let's see, you should have 0, right? The right-hand side is 0. So you have 4, right? You have minus 6, and you have 2, which add up to 0. Here you have 1, you have minus 3, and you have 2, which also add up to 0. Oops. Okay, so you got the left-hand side equal to the right-hand side. Means that this is your solutions, right? And it's general solution, by the way. Okay. All right. 420. Let's see. 420. 420. You got d cube y by dx cube minus 4d square y, right? Plus dy by dx plus 6y plus dy by dx plus 6y equal to 0. Again, what you have to check is linear differential equations, homogeneous, constant, coefficient, which is all of them pass. All right. So the next step is to find the characteristic equation. So to find the characteristic equations, you just take the order and put m instead of the derivative, right? So you have mq minus 4m squared plus m plus 6 equal to 0. Okay, how do you find m from me? So can you tell me what is m? First of all, how many m's do I have in this case? Factor, right? How many m's do I have in this case? How many m? How many roots do I have in this case? 3, correct? You're gonna have 3 roots. So we have third order. So you have m1, m2, and m3. Okay. How can we find those m's? Any suggestion? Oh, by the way, minus 2, minus 1, 2, 3. Okay, by the way, I would like to sorry. Okay. All right. I would like to go back a bit to 419, right? 419. Before we continue, before I forget, actually. So we have e to the power of x, right? This is the first one. The second one is e power of 2x. And we're going to see that those two are linearly independent by using the Wronskian. So this is how we calculate. So we take the first derivative, got e to the x, and then you get 2e to the power of 2x. Okay. And now when you find the determinants, you would get 2e to the power of e to the power of x times 2e to the power of 2x, and then minus e to the power of x, right, times e to the power of 2x. So this is 2e to the power of 3x minus e to the power of 3x, which is e to the power of 2x, not equal to 0. So it means that e to the x and e to the power of 2x, they are linearly independent. That's why we can make this, make this general solution. All right. Okay, before I forget. Now go back to here. You got m cubed minus 4m squared plus m plus 6 equal to 0. How can we find? How can we find the roots? How can we find the roots? Someone gets me like minus 1, 2, 3. How do you get that? How do you get that? 1, 2, 3. Minus 1, 2, 3. Anyone? Do you still hear me? Silent. Yes. Okay. So how do you get the roots of these differential equations? Oh, sorry, characteristic equations. Suggestion: synthetic division. All right. Fine. Let's do that. So if trying to put some numbers in, right? Say m equal to minus 1. What do you have? You're going to have minus 1 cubed minus 4, oops, minus 1 square plus minus 1 plus 6 equal to 0. All right. So when you evaluate this, you get minus 1, minus 4, minus 1 plus 6 equal to 0. And 0 equal to 0, which is correct. So what does it mean? It means m equal to 1 is one of your factor, right? By the way, how can I guess about this number? Actually, I get it from here, the last one. So for 6, you have the factor of 6 to be, let's say, 1 and 6, 2 and 3, okay? And you might need to try plus and minus for those number, okay? So here I try minus 1, m equal to minus 1, and I get the equations correct. So 0 equal to 0. It means that m equal to minus 1 or m plus 1 equal to 0 is a factor, okay? So I take this m plus 1 and use this synthetic division. Okay. So I need to put some terms here such that when I multiply this m plus 1, I got m cubed. Okay. So obviously that should be m squared. When I multiply m squared with m, I got m cubed. And when I multiply m squared with plus 1, I got plus m squared. And we subtract those two terms. The first term becomes 0, right? this is 0. And the second term become minus 4 minus 1 m squared. So it's minus 5 m squared, right? And we pull down this m. Again, we need to take some terms here such that when we multiply by m, you got minus 5m squared. So that term should be minus 5m, right? So we multiply minus 5m to m, you got minus 5m squared, and then minus 5m. And we subtract those two, you get m minus 5m, which is 6m, right? And I pull down here, plus 6. So the last number I would need here would be 6. So I got 6m plus 6, which is 0. And of course, if somehow you don't get 0 here, but you get the equation satisfied here, something wrong, all right? Either at this step or that step, something must be wrong. Okay, but here we get it right. So it means that we can write down mq minus 4m squared plus m plus 6, right, equal to m plus 1 times those terms. So it's going to be m squared minus 5m plus 6. And now you got this the second orders here. So you can factor that into 2 parentheses. Oops, this should be m plus 1, right? And that would be m minus 2, m minus 3. So in this case, your m would be minus 1, m2 is 2, m3 is 3. So your general solution would be c1 e to the power of minus x plus c2 e to the power of 2x plus c3 e to the power of 3x. And we're done. Okay. All right. So that's how we get the first case, distinct real root A. Now the second case is going to be repeated real roots. For example, you have d squared y by dx squared minus 6 dy by dx plus 9y equal to 0. So when you find the corresponding characteristic equations, you would have m squared minus 6m plus 9 equal to 0. Okay? And when you find the roots, you would have m1 equal to m sub 2 equal to 3, right? So it's still real, but repeated root, or you have the same number for m1 and m2, the same root. Okay, suppose we're going to go for general solution using this root, what is going to be? So your general solution is going to be c1 e to the power of 3x plus c2 e to the power of 3x, right? Which is obviously, they both are the same term, so we can combine them, right? And call that, let's say, c0 e to the power of 3x. And obviously, this is not a general solution, right? Because for general solution for second order, you're going to need to have 2 linearly independent. Okay? Here you have just one solutions. You have to find another one. However, this approach we have give us the same number. So we have to do something more. Okay. So what we do is we use reduction of order. Remember, we apply the order reduction theorem, or reduction of order. So this is what we're going to do, right? I just would like to put this. Okay, actually, I just followed this. So let's write it down for you, so it will be more clear. Okay. So you are given, you are given the differential equations, d squared y, right? Y dx squared minus 6 dy by dx minus 6 dy by dx plus 9y equal to 0. Plus 9y equal to 0. Okay. All right. And you are given one of the solution, right? Y equal to e to the power of 3x. Actually, you find already this solution from the, okay, let's say, find this from characteristic equations. Okay. So you need to find another linear independent solutions. All right. So what we do is we transform, this is y1, right? So we say y2 equal to f of x, which is y1 times v. Okay. So we take the first derivative. Okay, let's say I just drop the substitution, the subscribe here. So dy by dx would be e to the power of 3x times dv by dx plus 3e to the power of tx times v. Okay. And we also need to find the second derivative. Here you would have e to the power of 3x. And the second derivative would be, the derivative of dv by dx would be d squared v by dx squared, right? Here we need to take the multiplication rule. So it's going to be 3 times e to the power of 3x dv by dx, right? And then plus the last term here. So you're going to have 3e to the power of tx dv by dx plus 9e to the power of tx times v. Okay. Am I correct? Still correct or not? Let me see. Should be correct. Okay. So next, you're gonna substitute that back, right? So what do you have here is d squared y by dx squared, which is e to the power of 3x v double prime, right? those two terms would be 6e to the power of 3x v prime plus 9e to the power of 3x times v, okay, minus 6 dy by dx, which is e to the power of 3x v prime, right, plus 3e to the power of 3x times v, and then plus 9 times y. Y is e to the power of 3x times v. Okay. Okay, so what we have here. So here you're gonna have e to the power of 3x v squared. Oh, v double prime, right? There's no other term. And then plus, here you have 6. Here you have minus 6. Okay, so it seems like you have the 0 here. Okay, and then the last term here you have 9, and you have minus 18. You have plus 9. So again, seems like you have a 0. Okay, then you have the right hand side is equal to 0, right? This one. Okay, so now we have e to the power of 3x v double prime equal to 0. We can also divide by e to the power of 3x because that term will never be 0. So what we left is v double prime equal to 0. And we have w equal to dv by dx, right? So dx is going to be d square v by dx squared. Or this becomes these differential equations. So right? Okay, w will be integration of 0 dx, and oops, would be constant. Okay, or any constant. Any constant. Take w to be any constant. You get the derivative of the constant becomes 0. Okay? And we c equal to 1 here. So it w equal to 1. So v integration of w dx. So it's going to be integration, which is x. In that case, we're going to have y2 equal to, oh, sorry, some constant, right? In this, we're going to have y2 equal to x plus c sub 0 e to the power of 3x. Okay. This is the given equations, given solution, and here is v. Okay. So we have x e to the power of 3x plus c0 e to the power of 3x. But we already have those terms from the given differential given solution, right? This is just another constant times x. So this term will be not taken into account. So finally, you're going to have y2 equal to x e to the power of 3x. So in some summarize, first solution is this is come from the second one is x e to the power of 3. This is come from reason of order. So two has linearly we left that for you if you would like to test it. Okay. However, to condense, this is the Wronskian, right? As C1 e to the power of 3x plus e to the power of 3x. Okay. Or you can just put into this term. Now, the general solution for the repeated root. You put one more x here. So next time you do need to repeat this procedure, okay? There would be some theorems here. So this is what we have done. I showed you already. This we have get, okay? So if you have n other differential equations and you have the double real root m, so one of them equal to e to the power of mx and another one of them is x e to the power of mx. Just multiply x equations, and those two would be linearly independent solution. Okay. Now, suppose the roots of characteristic equations are double real root m and n distinct real roots. So you're gonna have those two are repeated, right? Okay. Repeated. And those, the rest, this thing, okay? So what is repeated, you have to put into this form. What is not repeated is from the first case we have done, right? It can be, you can have just two root repeated and the others not distinct. So it's the general solution you have to put on, okay? If it's triple, have m1 equal to m2 equal to m3 and equal to m, right? So you can put x squared the next term, right? So your solution would be c1 plus c2x plus c3x squared and then e to the power of mx, all right? Doesn't matter how many repeated root you have, you're gonna need to put x to the power of m until x to the power of n minus 1. N minus 1. N is the number of repeated root. Okay? So you have n order with m root occur k times. So you have to x squared until x to the k minus 1 for the general solution. Okay? If the roots are distinct, then it just go like it has before. Okay. If, however, any of the remaining roots of the general solution corresponding each of those repeated roots, as we have done before, So in conclusion, if you have roots which is consists of this thing repeated, your general solution would be this thing is going to be C2 e to the power of m2x, so on. For the repeated k times, this is going to be, let's say, plus cn plus 1 x plus cn plus 2 x squared until, let's say, cn plus k minus 1 x to the power of k minus 1, and then e to the power of this is mn, let's say. Okay, so if you have two parts, you're going to have the general solution for this thing and also, repeated, this thing and also repeated together. Okay. I will show you this first one, and let's say you're gonna need to find okay, let's show you this 4.22. So you have bq by dx cubed minus 4d square y dx squared minus 3dy dx plus 18y equal to 0. Okay. So this equation is linear differential equations with homogeneous and constant coefficients. So we can solve that by finding characteristic equation, and that would be m cubed minus 4m squared minus 3m plus 18 equal to 0. Would let you do it, and you're going to find that your m cubed minus 4m squared minus 3m plus 18. This is can be factored into m plus 2, m plus 3, and m plus 3. So in this case, you would have two types of roots, right? This is going to be real this thing, and this is going to be real twice. Okay, right? So this real and this thing, your m would be equal to minus 2. So and repeated, your m is equal to 3. So you have found the root. So you can write down the general solutions. So for this, I have C1, if you have C2 plus C3x, you have just, and then e to the power of from the differential equations here, you have to see that it is with constant coefficients. And then you can find the solution by first finding the characteristic equations And of course, this characteristic equation is just substitute the derivative with the m, right? So the third derivative would be m cubed minus 4 second derivative would be minus 4m squared and so on. Then you solve for m, right? This is cube, so you have to have 3 of the roots. And once you find the root, it seems you found that one of the root is real and distinct, which is m plus 2. The other two are real but repeated twice, so m minus 3. So m plus 2 would mean m equal to minus 2. And the factors m minus 3 would mean m equal to 3, right? So you have repeated for m equal to 3 twice. That would go for c2 plus c3x e to the power of 3x. And you have one real distinct root, m equal to minus 2. Let's go to the first terms here. So that would be the equations, the solutions. All right. I think we stop here. It's another one here. It's fourth order. It's quite, let's say, quite tedious. Let's just put it here. Anyway, so today we just complete 2 out of 3 cases. We complete the distinct real root case and also the repeated real root case. Okay. Any questions? Any questions? Silent. So no questions? Everything's clear? Or you still alive? Pick one. Hello, still there? Somebody's still alive? Oh, yes. Okay, good to hear. All right, so that would be it for today. And I will post the homework in the team assignment, right? You can see from there, and you can just write down in the homework the same you write down in quiz. Okay, and if some of you do not have the Apple Pencil, you can just go ahead, write down in paper, capture the picture from me, and just insert the picture in the homework. That would be also possible. Okay. Anything else? Any questions? Okay. Then see you next Tuesday, right? Tuesday. Okay. Thank you. Stay healthy until then, right? Okay. Bye-bye. I end the session now. Thank you.